Okay, I think that we switch directly to the hands-on session, and this is also about stimulation. So if there are any questions still, maybe we can also address them during the hands-on session. So please take out your notebooks again, and you will now simulate your own stimulation.
So this is the program for today. Oh. Yeah. Well, hello again. So I hope everyone's still locked into TVB, and I think we stopped somewhere here at the simulator page. So can you nod if everyone is there at the moment with us? Okay. Yeah, so you've seen this already. What we're going to do now is we'll create a stimulus and then apply it to our simulation from the first hands-on session. So to create a stimulus, you go to the stimulus page down here, click this button, and from the opening menu, you choose region stimulus. And this page you've seen as well. From this drop-down menu, here you can select one of the stimulus you've already defined. If you haven't done so, we will now, you won't see anything there, but we will define a new one. So give it any name. Just call it node number 6 again. Select the connectivity you want to apply the stimulus to from this drop-down menu. Again, you should probably only have the default John Doe connectivity there. And then we will set the parameters of the stimulus. So we will use this pulse train function with an onset of 1000. Tau equals 10 and t equals 100. And on the right side, you would see the temporal shape of its stimulus, but since the onset is larger than our scale here, you would have to increase the scale by plugging in something like 2000 in here or 3000, and then there it is. So the first second of our simulation will be run without a stimulus, and at 1000 milliseconds, we will apply this stimulus of the pulse function with an amplitude of 1. Now go to set region scaling, and we will apply this stimulus to the prefrontal cortex of the right hemisphere and the temporal cortex of the left hemisphere. So you can either unselect all by hand or just click this box here to unselect all the regions. And now let's select the first right prefrontal cortex pole here and apply a scaling, let's say, of 20, and then press set scaling. Now we do the same for the right temporal cortex central, but let's apply a negative scaling of -20 and press set scaling. Can everyone follow? So I just highlight them on my screen again.
So if there's a problem, raise your hand, please, again, and you will get help.
So in the end, it should look like this on your screen as well. This is LTCC, so left TCC, left temporal cortex, I think central or something. And then the scaling is -20? Mm-hmm. Oh, okay. So you should start now already. No. Yeah, something more than 1,000, like 2,000 or 3,000. 500 should probably be okay too, but the thing is I want to show in a second is we use the dynamics of the first hands-on session, or the same thing that Andreas just described, where we have those dynamics, but they fade out and we have a flat line after 500 milliseconds, 600 milliseconds, but then at 1,000 you will get this pulse, and then activity starts spreading through the cortex, which was dead. And now you can observe those patterns, how energy gets transferred through the system. So this is why not less than 500 milliseconds, I would say. Okay, so if everyone has found this region and set the scaling, then press this plus button, save this new region stimulus. And go to the simulator page. And here, so I have to start a new simulation by clicking on the star up here. Otherwise, this is, as explained before, this is the old simulation and the history you guys can see. Press the star and start creating your new simulation by giving it a name again. Let's call it stimulus. And then repeat the same pattern as before. Choose the connectivity. Again, you probably only have one. As long-range coupling function, we use a linear function with a equals 0.05. Conduction speed, before we used 16 millimeters a millisecond. And this time we will use the default settings just for this local dynamic model, the generic 2D oscillator. And remember, with this A equals -2, as I said, you can look this up in the faceplane viewer again and explore this dynamics. You will spiral down into this fixed point. This is what we were going to see in the simulation again, that we end there with a flat line. So point deterministic is okay, but increase the integration step size to 0.5. This will reduce the computation time. And again, use temporarily subsample with a sampling period of 1. Yeah? What? Yeah? For long-range coupling, A equals 0.05. But don't mix this up. They are both called A. A in long-range coupling function is the scaling factor, just a multiplication. And in local dynamic model, it's a different parameter. Yeah. I would have to look up the equations. I cannot tell you. Yeah, just take the default one, -2. That's okay. Just leave this unchanged. I would have, as I said, I would start a new simulation by clicking on the star up there. This will open up, you will stay on the simulator page, but it will open up a new simulation for you. Or you can take the old one and apply this stimulus there as well. The results should be similar. Good, so A equals 0.05, conduction speed 16. Leave the local dynamic model as it is. Increase the integration step size to 0.5, as here. Choose temporarily subsample with a sampling period of 1 millisecond. And set simulation length to something above 1,000 millisecond to actually see the stimulus applied to your simulation. And then press the play button. Okay. Could everyone follow? Yes? I forgot to to choose the stimulus. Yeah, that was my mistake. Sorry. Yeah, you were right. There's actually a drop-down menu where you will find your stimulus you just created, and you have to apply this to the simulation. I'm sorry. So to test if everyone's following. Yeah, just if you already started, the simulation should finish within a few seconds. Then just press this pencil near your old simulation and press copy. And then, of course, this will just copy all the settings from your previous simulation. And then from the drop-down menu, spatiotemporal stimulus, choose the one you just created. I called it Node 6. And then, again, press the play button. I'm sorry. Did it work? No. What I don't know. The stimulus was over it? Of course. Long-range coupling function is linear with A equals 0.05. The stimulus was overwritten. Okay. So onset was 1,000 milliseconds. Tau equals 10. And T equals 100. And then plus 20 and minus 20 to actually any region you want. You just can play around with this and see how simulation change. Okay, did the simulation finish? Shouldn't take more than a few seconds, actually. Yeah, then press, you would see the result on the right side by clicking up here, results, and select the time series region. Press the visualizer tab and choose brain activity viewer in 3D and 2D. So, and what we see here is, due to random initial conditions, we start somewhere on this phase plane, but as you can see, it oscillates and then ends in the fixed point. And now we see up here the time bar is progressing. We're now at 500 milliseconds, and our onset was 1,000 milliseconds, so soon we will see the stimulus being applied to our simulation. Sometimes in the time series, it's clearly visible. If you want to, and on the brain surface as well. So to make it more visualized, you can change the color range for your display, and then the oscillations will become more prominent. Also, the scaling can be adjusted for the time series on the right side, just by clicking up here on the right side, this brain symbol. Do you see something similar on your screens? Cool. So no, this is a similar paradigm of what Andreas Spiegler just explained. We're using an oscillator, which ends in this fixed point with a flat line, and now we give a stimulus. So here we're applying a stimulus to two regions at the exact same time. He was just stimulating one. And then we observe how the energy is transmitted. The only difference is that here we're just using region-based simulation and no cortical information.
Can you show again how you got to the visualizer?
Sure. When you're on the simulator page, on the right side you should see the result of your simulation. Time series region. Press on this and then use so here, time series region. visualizers. Visualizers, and then choose any. So I choose the 3D and 2D visualizer. And then you should arrive here. Did it work? So this is just a logged data. Like it's finished. Yeah, time series region is the one. Choose the visualizer and then you should see the result. Long range coupling, 0.05. Yeah, did it work for you? Okay, you're looking, so it was a question mark. Yes, of course. Oh yeah, this I think how the different areas get activated. Yeah, I think he did. Andreas, I think did PCA on this, and then observed this pattern. That's probably a good question for him. I think he used it first and second component of PCA. Mm-hmm. So actually, what he did is he stimulated an uncoupled region and got this time series, and then subtracted this from the coupled areas to get, and what remained was the energy from the stimulus on the other time series, and then he used this for his PCA. Of course, yeah. no, there's more, of course, math and technique behind this. So we have like 10 more minutes. Did everyone manage to run this stimulus? Some are still. Of course. Right. In the setting we have it now. Then we use this generic 2D oscillator with the same parameterization for all the nodes in our network. But as Paula showed you before, you can go to the faceplane viewer and save different configurations. We will do this later today in the hands-on session of epilepsy. We will save different configuration of the same local model and then apply it to different areas. And then they will behave differently and they will interact with each other. You will see this later in the last hands-on session today. So maybe another thing, as some of you have already finished, the last sections of Andreas' talk was applying this TDCS, which this direct current. I just want to show you how this can be achieved as well within TVB. You can use the same pulse train function and just reduce T, which is the interleave time, and you will create this current offset. At your onset time, you decide, and but then of course you are still missing the actual scaling values, which are derived in his paper or in this article, are derived through this finite element boundary model. And then, so this direct current is applied to different areas with a different scaling. Here in our setting, we just use 20 and minus 20 to two areas. Of course, there's, depending on where you put those electrodes, different areas get affected by the same stimulus in a different intensity. And So I'm just saying this so you can explore this maybe later on your own as well. If you want to run those simulations, you would also have to use a different local model, which is called the Janssen and Dritt model. So this is a more biological, sophisticated model which incorporates pyramidal cells and excitatory and inhibitory interneurons. Okay, this was it for
Thank
the
you, Paul.
hands-on session.